My name is Katie. I work on the scheduling APIs team at Google in San Francisco. And today I'm going to talk about an analysis that we did on input latency. More interestingly, we used a lot of trace data to do this. So yeah, that's the topic. Okay. Oh no, it got all mucked up. All right, well, so why do this analysis? I think it's interesting to start with, but the goal of the analysis was to identify the top contributors to input latency. So once an input event hits the main thread of the renderer, what is contributing to that event not being displayed on the screen fast enough. For our team's interests specifically, we wanted to find scheduling use cases, so opportunities where we can improve performance with scheduling, so optimization opportunities. That was sort of just a side goal, though. The main idea was what is causing input latency in the renderer. Okay, so I'm going to start by talking about the analysis, the process, and the tools that we used. And then later I'm going to talk about what we learned and go into some interesting outliers that we found. So this analysis was done using something called slow reports. It is a infrastructure that collects trace data from real-world users. There are two types of slow reports, deep reports and bulk reports. Bulk reports are collected on users whether or not they opt in, and deep reports are collected on users who explicitly opt in their Chrome settings. So trace data is collected when you do something like navigate, that gets sent to us, and then we have it in cloud storage. We can just access it and look at it whenever we want. So we did this analysis using deep reports, which means that we're only looking at users who did opt in. That's worth mentioning because the users that opt into this tend to be developers or, the type of person who would mess around in their Chrome settings are probably not wholly representative of a typical user. So that's some bias. We also decided to look specifically at Android traces for mobile focus, and we were looking at input latency events that were greater than 100 milliseconds. This comes from the Rail guidelines for user perceptible input delay or latency. And so we took slow reports and we piped them into something called the Chrome trace processor pipeline, which exists in Catapult. Here you can have a model of a trace that you can call functions on and process with JavaScript. I think deep reports and slow reports are being deprecated. So this is not like a replicable analysis, but yeah. So once we got the traces into the pipeline, you write a mapper to run on them. This mapper can extract information from the traces. You can look at the event slices on the traces. You can look at anything that you can see in the trace viewer is represented in the mapper you can access. So this mapper iterated over all of the traces, which I think in most cases was around hundreds of thousands, like 400,000 traces, and looked for traces that had input latency events that were longer than 100 milliseconds. And it also looked for specific, this is on 400,000 Android traces. We looked for input latency events that were longer than 100 milliseconds. And then we iterated over those input latency events. And we looked at all of the things that were happening on the main thread of the renderer during the latency. So the idea was, what is the renderer doing when it has this input event that it could be handling? What is it doing instead of handling that? And what is causing the delay between when we start to handle the event, when the renderer receives the event, and when we commit the frame? Okay, so this is an image of like an illustration of a trace. A couple points here. Our definition of the start of an input latency event was when the input was dispatched to the renderer. So this is when the browser forwards the input event to us. We broke it down further into the queuing time and the handling time. So the queuing time is when we had the input event and we hadn't handled it yet. And then the handling time is from when we had started the handling and to when we committed the frame. So those were our beginning and ending for our latency events. We only looked at the render main thread. And there's another thing that we did here, which was we created an event slice, which is the idle time. So there are times between events on the render when the render is not doing anything. And we wanted to capture that as well, because if the render is idle during an input latency event, that's also kind of interesting to us. So that is sort of the overview of how we broke this down. We took two approaches when we were looking at an input latency event. We went from the bottom up and we looked at the self times of each of these events. So that is just like for event A over here, the self time is just this little sliver. And so that gave us a view of what's happening at the lowest level of the trace. I call it the event tree because it kind of looks like a tree to me. And then we also did top down, where we were trying to find what events call into the lower level events. So oftentimes if you look at a trace, the bottom level is script. And we kind of wanted to see, okay, well, if we're spending most of our time in script, what is calling that script? So that was the general idea of our two different approaches. And then the last step, we put all of this information into a Python script. So we took all of the self times of these events and we summed them across an input latency event. And then the Python script would take all of these event durations and calculate the average across all of the latencies that we looked at. So for each event slice, take v8.execute, for example, we would sum all of the v8.executes on all of the latencies, and then we put that over the number of times that v8.execute occurred across all of those latencies. And then we took percentiles at all of those durations. And also we calculated the duration, the summed duration of v8.execute over all of the latency events that we looked at. So we have kind of the intersection of how often this event occurred and how long it was taking as well. And so then we took the top 20 trace events by average duration. This is the number of like the duration of the event over the latencies in which it occurred, and we visualized it. So this is getting into the output. So if you want to look at the data, it's all the data and the graphs are on this Git page. But this is an example graph that was outputted for gesture tap bottom up. So these are all of the self times for the top 20 longest events on average for the gesture tap latency event. So this is supposed to be kind of giving us the idea of what an average latency event looks like, an average gesture tap latency event. So some things to note are mostly that we found the queuing time is smaller than the handling time, which is sort of expected. A lot of the handling time is spent in actually handling the event, surprise, surprise. And most of the latency comes from doing script. So this big pink section is v8.execute. So we've got a lot of script doing going. Another notable thing is this pink chunk right here is idle time. So there's actually a surprising amount of idle time during these latency events, which we found surprising because why would the renderer be idle if it has work to do? And so I'll get into some of the cases about why the renderer would be idle when there's work to do a little bit later. But yeah, so this is all on the web page. There's a bunch of these graphs for various latency events. But we see the makeup of a latency event is kind of what you would expect. If you're handling input, you're going to see some layout work happening. This is also, all of these events are only events that will actually cause a layout to happen or a new frame to happen. So as expected, you see we're doing layout work. We're running microtasks, we're painting, there's some garbage collection that happens, some hit testing that happens, a lot of things that you would expect, and also some things that you wouldn't expect. Some things that bubbled up to the top were sending pending accessibility events, which is kind of surprising. And I'll talk about that a little bit later, about why that's up at the top. That's the problem with averages. Some Blink ATX tree source serialized node also bubbled up at the top. So some things that we were like, what? Why is that there? We didn't actually know. Okay. So we don't have a visualization for, I talked about the averages over all of the latency events instead of just the ones where it occurred. So we also calculated that. We didn't visualize it, but it's here. I don't expect you to look at all of these numbers because it's kind of crazy. So I'm going to point out a few of them. V8.execute, which is our biggest contributor script, runs kind of in every single trace almost. So for gesture tap, I think that this was, if I remember correctly, 20,000 latency events about. So there's a pretty even spread at every percentile, how long V8.execute is running. So that is sort of expected. The median and everything is about, the 99th percentile is kind of shocking because we go up from 336 milliseconds to 2041 milliseconds, which is a lot of time to be spending in script. You'll also notice from this that we were looking at latency events that were 100 milliseconds, but on average, the latency event took like 400 milliseconds. So that's pretty surprising. Anyways, this is V8.execute, as expected. Pending accessibility events, which I mentioned earlier, actually doesn't take that long in most cases that we see it. But when we look at the data this way, we see that in the 99th percentile, it's taking a really long time. So something about this callback, when it happens and it's bad, it's really bad. Bad enough that we're seeing it as one of the top contributors to input latency. So this would be an interesting thing to investigate in the future. Okay. So idle time, which I promised to talk about. We also wanted to see why idle was happening so much. There's kind of an expected amount of idle time when you're going from running one event to running another event, which is what you see at the lower percentiles. It should be really, really tiny. But at the 99th percentile, there are times when the render is just not doing anything. And we thought that was really strange. Why would the render not be doing anything when it has input to handle and a begin mainframe to run? So there were a couple reasons for this. We actually pulled down some specific traces. This analysis was kind of batch processing traces, but with the mapper and the pipeline, we were able to say, okay, we want to look at traces where we have an input latency event and the render is idle for a really long time during that input latency event. Just to sort of see what was going on. So we pulled down a bunch of specific traces and we looked into some of them. And I'm going to talk about two of the outlier cases that we have, but of course there were more. So the first case that we have, this is an image of an actual trace. This is the input event handler, which is, like I said, when we say the handling time starts. So we get the input event kind of at this boundary here, and then we handle it pretty soon after we receive it. There's some scoped blocking call, which is kind of like a scheduling thing that is running code that we can't interrupt. It's usually input or IPC messages, I think. And then we do the input event handler. So as soon as we can, we handle the input event. And then we have a bunch of time that we're not doing anything. And way over here is the associated frame commit. So, I mean, you can read the title of the slide. We're waiting on a raster. So if you go down from where you see the main, so this is the main thread. If you look at the compositor, you see the compositor is doing this thing, pending submit frames. So it's waiting on something before it submits the frame back to the main thread, where the main thread is then going to commit it. And if you go all the way down to the GPU, you see right here, there's a raster happening. And we actually brought this up to N, I think, and they said that this should never happen. The raster should never be this long. And they have metrics that measure rasters. And this is like a 99.9th percentile case. This shouldn't happen very much, but when it does, it can be really bad. And we learned from that this didn't merit further investigation from them because it happens so rarely. But it would be really interesting to see why we're getting stuck in a raster. I have no idea. So if anybody has any idea, that could be interesting to hear about. Okay, and then the second case we learned about is actually the render input latency event tracked across a navigation. So here is our handler. So we get the input event somewhere here. We handle it here. And then once again, we see a long idle period. This is during the handling time before we commit the frame. And so we were like, what's up with that? I did check the compositor and the GPU. There's no raster going on, so something else was happening. So I looked at the use case. I think we actually sent this to the scheduling folks, and they were like, well, the use case here, you see 2 loading periods, which you really should only see 1 loading period per page, right? Because you're only ever loading a page once, which means that there's probably navigation happening. And if you go up to the net log, there was a URL request. So we started an input latency event. We got the input, then we did a navigation, and then the frame for that input was committed after the navigation finished. It was kind of weird. We did follow up with some folks, but I don't think we ever really determined whether or not this was a bug or where this problem was happening, because it's really hard to replicate. But this boundary kind of says the start of the input latency event, and the URL request comes in before the input latency event starts. So I'm not really sure if the input triggered the latency event and then was tracked across a navigation and then the frame was committed, or we started a navigation, did an input, the frame was committed after the navigation was finished, and we just didn't just do anything with it. Not really sure. So those were 2 interesting cases of the render being idle that could merit further investigation. Okay. So what we learned from this is that you can learn a lot from traces. There's this whole large amount of trace data that we aren't really doing anything with, that you can do things like bulk process traces, and it's real world data. So you can like find really interesting edge cases. I think Etienne is working on, he has his own pipeline for processing these traces and picking out specific traces and investigating specific bugs that he finds in them. But I think that's the only work I know of that is actually doing stuff with these traces. It can guide us where to focus our efforts. So the rendering, the send pending accessibility events thing, maybe it's worth investigating for the accessibility team. At the 99th percentile, that kind of delay is really bad. So that could really improve user experience for some of our accessibility users. And we can also find general trends in the data when we process in bulk like this, which is pretty interesting. There's not a lot of like infrastructure that's maintained for doing stuff like this. I think the Chrome trace processor pipeline and the bulk reports are being deprecated, but there's going to be more work on Chrometo, which might help us do some of the things like this. I don't know, Oystein can talk to that. But yeah, another thing is when we were doing this and more for scheduling related stuff, we had questions about microtasks, and like one of our first responses was, okay, well, where are microtasks being called in the wild? And so I ran a mapper with the Chrome trace processor pipeline, and we got some data about microtasks that helped us like facilitate our discussion about making scheduling decisions around microtasks. So I think this kind of tooling can be really useful if you just have a general question about how your code is performing in the wild. So yeah, like I said, slow reports is being deprecated, which is sad because it is a really great resource of real world data. I don't think that we often have opportunities to use and look at real world data like this, other than like UMA, which is great. Yeah.
Yes, it's definitely happening. Right on.
Yeah.
Larger scale. So channel, and you can post process it. So let's talk.
That's good to hear. So yeah, like I said, we did stuff with microtasks. I think everybody has questions that they could probably answer with looking at this trace data. We also still have a lot of data from this analysis that we don't completely understand because it's out of our wheelhouse. So looking more into what we did find and the data there is another next step to have. So yeah, that's it. Does anybody have any questions or thoughts?
How did you find the course of this progress? You said there is a render IO and you didn't know why. So, but you found the GPU is slow or navigation might. So how did you find it?
Okay, the only way to find that is to look at actual traces. So I pulled down, I think maybe like 20 or so traces, and I opened them in Trace Viewer, and I just looked at them. You scroll around, you look at what is going on the other processes. Sometimes there's like workers running script in the foreground that seems to be causing latency, that kind of thing. So you just kind of have to visually identify it. I think it would be really interesting to find ways to identify it automatically. But yeah, I just did it the old-fashioned way.
In regards to the navigation, if you want to see it actually happen, if that navigation is actually happening, you may want to add navigation category to your trigger.
Oh, yeah, I think for deep reports, it is by navigation. So the trace is collected after you navigate, and then it goes. Well, I think it's supposed to go for 30 seconds or until you start another navigation. But so I have no idea how this happened. But yeah, also the deep reports have all of the trace categories enabled, which is why they're opt-in only, because it has a lot of information that can be user identifying and privacy information. So
if the trace has a navigation category, there might be a slide that indicates some navigation events on further process. So maybe you might want to check.
thanks.
I guess it'd also be in maybe like a software modification or something, because I think we only do a new trace on top level things, like the task, the whole targets navigated.
Yeah, I think I was talking to Nate earlier. We were saying it might have been same origin navigation, so that's why we're able to trace a latency across a navigation.
I'm curious actually if the Microtasks have any like so this was a lot of work. This analysis.
Yeah.
It was a lot of work. It was more work than any of since when we started on. And that's not a criticism. The fact that it exists at all is amazing. But I feel like Komodo has the promise of a lot less work. But I don't feel up to date on like timelines of when we can get this stuff.
So I think a lot of this functionality will come for Q1 in addition to when. Like it was fun to see your presentation. Like yes, this is great. It made me very happy with this exactly working on it. So basically, new trace viewer has a built-in SQL engine, so you can like for each individual trace, you can run any kind of like fancy, like I want timeline from here to here, or like I want a history of this value for this specific trace, but then you can run the same thing over every trace.
Cool.
And then you can aggregate all of that. So I think this will fit really well into this kind of analysis, and you don't have to do the pipeline part. You don't have to because like a lot of this you will just get for free in addition to like aggregation across applications. okay, what's happening when this trace event happened, what's happening elsewhere in the trace that we feel like told stats or so yeah, yes, this made me very happy to see that this might be very helpful.
It's good to hear that it'll be mostly built into Chromato. That makes me happy. Will there be, the mapper that I wrote was all JavaScript. Is there going to be a way to run JavaScript on these traces?
So we kind of want to go all in on
Queries.
SQL and Microtasks. Like this is a very good engine for querying data within traces, so a lot of it is probably there. There are like you could write some stuff in like C++ and pipeline, but hopefully you should be able to do a lot of this stuff just using pure SQL over each individual trace, and then we take on the aggregation part for you. So you can still, and then you can still, of course, like, go into individual traces. Okay, you can, and then in addition, so I sometimes when you did, I'm sure, the investigation, you're like, oh, this type of traces are not helpful. These are very helpful.
Yeah.
There's also a tagging support where you can do the same of the query and like only these traces should be included in the data that allows you to include and exclude a lot of traces, but just like whatever you see visually, if you can express that in SQL, then we can use that to like remove or add traces into whatever you look at in aggregations.
The main difference would really just be that since we're scaling up to like later channels, we're much more constrained in data we can collect.
Yeah.
Like these traces are like full detail, everything.
Yeah.
Just because they're just stuck in every. The Camilo stuff, stuff that like you'll have to approve. So like the base trace events are fine, right? Like the names, when they start, the duration, all that stuff. We can have all of that, but like if you want more per event data, like that sort of basically needs like logs approval and stuff. But after that point, as long as the data is there, like yeah, we can do exactly the same.
Yeah, we chose deep reports because it had we wanted to see everything that was happening on the render, and the only way to do that was with everything enabled. So
One thing we're a little bit the good thing is that since we can do a lot of this after having uploaded the traces, we have like raw traces. You don't have to necessarily do like if there's a metric you can calculate afterwards, you can just do that in the pipeline instead of having to go back to Chrome and like, oh, I need to add a new metric from here to here. Like you can just calculate it just like you did in like the Python script. So you can do that in the pipeline instead. So roll out a new stable version is fine.
yeah, well, it's gonna get easier to do this kind of thing. So everyone should check out Chromato. But yeah, any more questions? Cool. Well, I think we're basically at time. So thanks again.